And currently, the industry is trying to solve these variability issues purely through material science. They're spending millions trying to figure out how to deposit the MOS2 more uniformly or engineer the atomic defects perfectly.
But what if we combine the fields? What if we stack Ollie's inverted MML patent architecture on top of that existing ASIC tech?
This is where it all clicks together for me, because it means you take the burden of physical perfection completely off the shoulders of the materials science engineers.
Exactly. They don't have to build a perfect MOS2 memristor anymore.
You build the atomic triad using those highly efficient but highly variable MOS2 memrisors. Then, the inverted ML digital controller dynamically calibrates out the spatial mismatches and the thermal drift that currently plague those 2D materials.
The software layer accommodates the hardware's flaws. Matrix 3 and Matrix 8 would intrinsically learn the specific, nonlinear quirks and atomic defects of that specific chip's MOS2 layer.
That's amazing. They would adjust the forward pass math to compensate for those exact defects in real time at full analog speed.
You basically get to have your cake and eat it too. You get the 53 attajoule energy efficiency of the 2D materials, but because of the MML control layer, you don't sacrifice the strict mathematical determinism required for accurate AI inference.
It creates a true symbiotic relationship. The hardware provides the ultra-low power O of 1 time calculation speed through raw physics, and the algorithmic architecture provides the digital determinism to keep the math clean. It completely bridges the gap.
It fundamentally changes the design philosophy. The hardware engineers can focus purely on speed and energy efficiency, pushing materials to their absolute physical limits, knowing that the inverted MML software layer will catch the errors and smooth them out.
It is such an elegant vision for the future of hardware. So let's just step back and look at the whole picture we've painted today. We started with the von Neumann bottleneck. The stark realization that moving data back and forth from memory to processor is bankrupting our energy budgets.
Which led us to the brilliant but inherently chaotic promise of analog in-memory computing.
Doing the math inside the memory using Ohm's and Kirchhoff's laws saves massive energy, but it traps us in a precision wall of voltage droops and thermal drift.
And the industry trapped itself further by using brute force complex routing and massive 2T2R cells just to fight the physics.
Until we unpacked Ollie's summer 2026 desk product, the Inverted MML Manifesto.
A hybrid system, the atomic triad. Matrix 33 doing the heavy lifting, with Matrix 3 and 8 using built-in proprioception to feel and correct their own flaws at high speed, entirely in the analog domain.
Governed by a sparse digital controller that uses brilliant hardware anchors, the 78.4% sweeping reference cells, and the synchronous 9.52% drooping bias cells.
Right, taking a few snapshot of those anchors to calculate the drift, circumventing the need to constantly monitor every single memristor.
And while there are massive unanswered questions in 2026 about duty cycle bottlenecks and where the system breaks at the 32 by 32 matrix scale, the roadmap is incredibly clear.
Stacking this algorithmic compensation on top of emerging 2D materials like MOS2 could unlock just unprecedented AI processing efficiency.
It completely flips the script on how we design computer chips. We don't need perfect hardware as long as we have perceptive software.
Which leaves us with one final thought to mull over as we wrap up this deep dive.
Let's hear it.
For decades, since the very dawn of the digital age, we have assumed that the absolute pinnacle of computing is perfect, flawless digital state maintenance. We have worshipped at the altar of the pristine binary 1 and 0.
Right, we want our machines to be exact.
But as we look at the human brain, which is still, by orders of magnitude, the most energy-efficient, powerful computer in existence, we know it doesn't work like that.
It's messy.
Exactly. The brain operates on noisy, degrading, chemically imprecise analog signals that constantly self-calibrate and adapt. If inverted MML succeeds in bridging the gap between digital determinism and analog chaos, it raises a profound question for the future.
What's that?
What if the next leap in artificial intelligence isn't about building ever more perfect, rigid hardware, but about designing algorithms that finally allow our silicon to be perfectly, beautifully imperfect?
Wow, imagine that. Letting our chips finally act a little more organic. Well, thank you for diving into the mechanics and the math with us today. Keep questioning the perfect grids, and we'll see you next time.